Hi everyone. So previously we had discussed on the topic Euclidean algorithm, right? So now today let's discuss the topic extended Euclidean algorithm, right? So this is the extension to the normal Euclidean algorithm that we previously discussed, right? So let's see what the definition part says here. So here the extended Euclidean algorithm computes the greatest common divisor GCD of the two integers a and b and also finds integers x and y, right? So the extended algorithm, Euclidean algorithm, what it does, it computes the greatest common divisor GCD of the two integers a and b and also finds integers x and y such that a into x plus b into y equals GCD of a comma b, right? Without coefficients, right? So this is fine. It's an extension of the standard Euclidean algorithm that returns the coefficients for the linear combination right? So here the only thing, so extended Euclidean algorithm computes the greatest common divisor. This is fine of two integers a and b, and also finds the integers x and y, right? Such that a into x plus b into y is equal to GCD of a comma b, nothing but without coefficients, right? So this is fine. Now let's get into the explanation part. Man, let's see the classic this one Euclidean algorithm previously we had discussed, right? The classic Euclidean algorithm repeatedly replaces a comma b with b comma a modulo b, this one until b becomes zero. We know this one. The last non-empty zero is this one. A is the GCD. The last one we had discussed, right? So we know this one correctly. Yep. Now the extended version keeps track of how many this one how to express each remainder as a linear combination of the original A and B, right? So again, listen to this carefully. The extended version, what it does, it keeps track of how to express each remainder as a linear combination of the original A and B, right? So by propagating these coefficients through the steps, actually, we obtain integers x and y satisfying a into x plus b into y equals GCD of a comma b, right? So this part is very important. Yeah, the same thing will be articulating in the form of code. No need to worry. So this is specially useful for computing modular inverses. So next we'll be moving on with the modular. So we'll be discussing modular inverses, modular exponentiation, these algorithms and all. So you have to, or we have to know the this one Euclidean algorithm and extended Euclidean algorithm at any cost, right? So basically, if the problems, suppose if you are doing CP, right? So you will be the questions will be based on the modular this one number theory. There are the questions will be based on the number theory at any cost, right? So you have to know this one Euclidean, extended Euclidean, and for the at least most of the times the tougher ones basically which are completely based on modular exponentiation. Basically, we will be if we are making use of modular exponentiation and this one modular inverses basically, right? So that's some theorem I forgot actually. And within the modular inverse we make use of some theorem, right? What's the theorem named? Actually, I forgot that theorem. So basically, you have to know this one Euclidean and this one extended Euclidean. So when we discuss this one modular inverse and modular exponentiation, let's see that one later actually algorithms. Yeah. So first, let's concentrate on this one. So this is especially useful for computing modular inverses if GCD of a comma 1 is equivalent to 1 value 1, right? So then x returned by this one extended Euclid is the modular inverse of a modulo m, nothing but possibly after reducing x modulo m, right? So this is fine, I believe. Let's try to implement the same thing in the form of code, man. Let's start writing the algorithm here by making use of the Python programming language. So I'll just go with the def here, extended GCD, extended GCD of a comma b. This is fine. Then let's go with the base case first. What we discussed actually, when b is zero, meaning the value b, if it is zero, then GCD is a, right? Coefficients are 1, comma 0. We know this one because we'll be going with a into x plus b into y. So this one, just keep this in mind. This part is very important. Yeah. So we will be going with a into 1 plus b into 1 because coefficients are 1 and 0, right? So when b is 0, we'll be going with a into x plus b into y, nothing but a into 1 plus b into 0. That is equivalent to the a, right? The coefficients are 1, comma 0. So directly when if b is 0, GCD is a. right? Coefficients are 1 comma 0 because a into 1 plus b into 0 is equivalent to the a, right? So I'll just come here. So this one, let me write the simple if condition here. If b is equivalent to the 0, then let's do one thing. I'll just return here a comma 1 comma 0, a comma 1 comma 0, right? So this is fine. Now let's go with the recursive call here. Let's compute or calculate the GCD and coefficient for b comma a modulo b. So what we discussed here, first let me uh, assign this one. Uh, Consider a as well as x1 as well as y1. So let's call the, or let's recurse here. So what we have made is of here function name extended GCD, right? Extended GCD of, so what are the things that we need to pass here? B comma a modulo b, right? Accordingly with what we have discussed, right? So we are just making the recursive call here. We are just computing the GCD and coefficients for b comma a modulo b. Yep. So this is fine. So one more thing, at this point, b into x1 plus a modulo b into y1 is equivalent to the g. Just remember, this is very important. Yeah. So now what we will be doing, we will be updating the coefficients to express g as a into x plus b into y, right? So a modulo b is equivalent to the a minus a by b into b, right? So see here, x, let me assign this one to y1 and y equals, so what I said, a modulo b is equivalent to the a minus a by b into b, right? So this one I can just write it in this way, x1 minus uh, this one a by b into y1 accordingly with what we discussed, right? So this is fine. Now what we have to do, now a into x plus b into y is equivalent to the g, right? So we have to return g, x and y respectively, right? So I'll just go with here return. So this is fine, I believe. Yep. One second. Return. What are the things we need to return? G as well as x as well as y. Sorry, just y. Yep. Now we are done with the algorithm. So this is it for the algo, right? Simple one. Now let's go with the example usage. So let me take the example usage from the Google Map. Just give me a second here. So here I have considered A, the value of A 240 and the value of B 246, right? So gxy we are just calling the this one extended GCD function here. All we have to pass is A and B, right? So this one 246 and 46 numbers basically, right? First what we are doing, GCD this one we are going with this format A B G. Then we are going with the coefficients actually x equals y equals format. We are going with the format x comma y. So next we are checking this one basically, right? So format a comma x, this one b y, a into x plus b into y. See, let me explain you what is the output that we need to get. I hope the algorithm part is completely clear. We have discussed this one step by step. So output, first thing, we are going with this one normal GCD format a, b and g, right? So GCD of what we are going 240 and GCD of 46 actually. What is the GCD this one? We have to get 2 actually here. In this case, we have to get the output 2 for the first print statement, yeah, by considering this x1, this one as the example. A and B value 240 and 46. We have to get output 2. And basically, the greatest common divisor or GCD of 240 and 46 is 2. You can just see, right? So this is fine now for this print statement. Let me write this one over here. So for the first print statement, we have to get GCD of 240, this one, in this case, GCD of 240 as well as 46. What we need to get here? We need to get 2. So this is fine. Yep. Now let's go with the coefficients. Next one, we are going with the coefficients, right? Coefficients actually, x we need to get, what we need to get here? X we have to get -9 actually, and y we are going with uh, x and y we are going with, right? So x -9 and y 47. So y we have to get here x -9 and y equals 47. So there is one valid pair of Bezout coefficient accordingly with the algorithm that we have written. Yeah, if you remember that the same thing we had discussed in the explanation part as well. You can just check. Yeah, one valid pair of Bezout coefficients is x is -9 and y equals 47, right? They satisfy actually what they satisfy here. They satisfy 240 into minus 9 plus 46, this one into 47, right? So this one will be equivalent to the 2 actually. You can just check. You can just check. So this is 240, right? So this will be equivalent to the 2. Whatever I have written here, this will be equivalent to the 2. So this is 240. Man, don't get confused here. Sorry. So this one 240 into minus 9 plus 46 into 47 actually. Plus 46 into 47, right? So this is fine. Yeah. 240 into minus 9 plus 46 into 47. This is equivalent to the 2. Again, one valid pair of Bezout coefficients is x equals minus 9 and y equals 47, right? So they satisfy 240 into minus 9 plus 46 into 47, which is equivalent to the 2 here. So this part, this is fine, I believe. So GCD of 240 and 46 is 2. And here, one valid pair of Bezout coefficients is x equals 9 and y equals 47. I have said you 240 into minus 9 plus 46 into 47, which will be equivalent to the 2. So coefficients we have to get x equals minus 9 and y equals 47. For the second one, we have to get this answer, right? So this is fine. So for the third print statement, we are checking this one here. This one into, we are going with this format, right? So the printed arithmetic basically verifies the identity a into x plus b into y is equivalent to the GCD of a comma b. Numerically, it will be, so numerically it will be, so when we do this, it has to be actually 2160 2160. This one has to be minus actually, and this one 240 into minus 9, 2160 minus 2160 plus 2162, right? So this one has to be again 2. This one has to be again 2, right? So here in this case, output we get as 240 into minus 9 plus 46 into 47 is equivalent to the 2. So this output for the third one, we have to get this output 240 into minus 9 plus 46 into 47, which is equivalent to the 2 actually. This output we need to get for the third one. We need to get for the third one. For the first one, this one print statement. For the second print statement, this one. And for the third print statement, we need to get this output. Yeah. Now I hope this is clear, man. So I hope the algorithm is also clear. So this is just the this one extended version of the this one. What do we call Euclidean algorithm? Yeah. So somewhere, so this one I have done wrong, I believe, man. So what I uh, gx1 y1, this is fine. Next we are going with x equals y1. Yeah. So this one, why am I giving this one in the same line? Y equals x1 minus a by b into y1 actually. So this is fine. Now as we have complete understanding of the algorithm, let's do one thing. Let's run the code man. Yep. So I'll just give Control J, Python followed by this one file name.py. Okay. This one invalid syntax extended GCD of a modulo b. Why I have given colon here? Let me remove this one. Yep. Now let me give clear screen. Let me run this one again. Yeah, GCD of 240 and 46 as per discussion. As per the discussion. So this one we are getting 2. For the second one, coefficients are x equals minus 9 and y equals 47. As per the discussion, this is also correct. Yep. So for the third one, we have to get this one, right? So we have to go with 240 into minus 9 plus 46 into 47 Bezout coefficients, right? So this one, which will lead us to the output 2. So we are getting the correct output coefficients as well as the check. So we are getting the absolute correct output, meaning we are getting the desired output, right? So I hope the algorithm part is completely clear, man. So this is the extension to the normal, this one Euclidean algorithm. Yeah, very simple. Yeah. So this is the extension to the this one normal Euclidean algorithm. So we are done with the mainly Euclidean algorithm and extended Euclidean algorithm, so that we can move on with the modular this one modular arithmetic, this one what do we call algorithms, basically that's based on the modular arithmetic, right? Modular inverse, modular exponentiation algorithms, those kind of things. Yep. So I hope the algorithm part is completely clear. Now, as we are done with the algorithm, let me do one thing. Let's quickly discuss the this one summary part. Actually, let me summarize whatever we have learned so far. Yeah. So just give me a second here. 1 second. Yeah, there are some 3 to 4 points that we have to remember at any cost. So I wanted to discuss with you guys, right? So let's start discussing the same. So now the extended Euclidean algorithms algorithm returns the GCD of A and B and integers x comma y with A into x in this one with A into x plus this one B into y plus B into y equals GCD of, for the GCD I'll just write G here, GCD of A comma B, for the GCD A comma B. So this is fine. Now let's go with the second point. So it works by recursively applying the this one Euclidean algorithm. This part is very important. It works by recursively applying Euclidean algorithm, right? So Euclidean algorithm. Yep. So it works by recursively applying the Euclidean algorithm and updating the coefficients to maintain the linear combination. We know this one. Yeah, you have to know this one at any cost. It works by recursively applying the Euclidean algorithm and updating the coefficients to maintain the linear combination, right? So this is fine. Now let's move on with the third point. So here, let's discuss some of the use cases. So computing GCD, solving Diophantine equations, and finding the modular inverses when GCD equals 1, right? So these are some of the use cases, right? So first one is computing GCD, for computing GCD, right? So the third one, the second one here would be this one, solving Diophantine equations, right? Diophantine equations. So this is fine. And the final one is finding modular inverses when GCD equals 1, when GCD equals 1, right? So this is fine. So these are some of the use cases. And the final point I want to discuss here is, so complexity basically. It runs on again because of the same thing, log of mon of A comma B, same as this one, normal Euclidean algorithm, right? So it runs in because of log of min of A comma B time. So same order as the Euclidean algorithm. Yep. So these are some of the points that I wanted to discuss, right? So these are some of the important points basically. You have to know, right? So this is fine. Now we are done with the this one extended Euclidean algorithm as well, right? So next, what shall we discuss actually? Next, we are done with the sieve of Eratosthenes, segmented sieve algo as well, Euclidean algorithm and extended Euclidean algorithm as well. Next, let's move on with the modular exponentiation as well as the modular inverse algorithm. These two, modular exponentiation algorithm and the next, after the modular exponentiation algorithm, let's go with the modular inverse algorithm, right? So for these two, we have to know the this one Euclidean as well as the extended Euclidean algorithm at any cost, right? So I hope the algorithm is completely clear, man. I hope the algorithm is completely clear, right? So we are done with the algorithm for now. This is it. Thanks for watching, guys.